Hey everybody, today I want to talk to you about Hooke's law, which describes the spring force, and this accompanies your textbook Matter and Interaction section 2.6. But because I wanted to jump the gun a little bit, it also covers some sections in some topics in section 4.11 in chapter 4. Okay, so first of all, to remind you of Hooke's law, this is a spring force. So if you're familiar with spring forces at all, just from personal experience, you'll know that if you stretch a spring from its equilibrium position, if you give it a tug, for example, then it'll want to go back to that equilibrium position. And if you, instead of stretching, compress the spring, then it'll try and push back out to the equilibrium position. So it's always trying to restore itself to its unstretched or uncompressed position. That's why the spring force is sometimes called a restoring force. If you displace a spring from equilibrium and then you let it go, then what'll happen is it'll oscillate back and forth between minus x and plus x here. So in this picture you can see here, the spring's been pulled to some position, x, and then what'll happen is that spring will bob back and forth between plus x and minus x at its extrema. So let me show you a few things. I have some FETs and simulations on springs. This is a nice FET on the spring force. And what you're looking at here is a pulley, or a pull, so you can pull on it like this, okay? You can pull on your spring. And when you do that, it's like grabbing it by your hand and pulling it on this little piston thing, okay? Now, to describe some things, this dashed green line right here is the equilibrium position of the spring when it's not stretched. And then when I pull on it, right, I'm stretching my spring out. The blue arrow that you see in the simulation is the spring force. So since I'm pulling it and stretching it out, the spring wants to go back to its equilibrium position. So if I pull to the right, the spring wants to go left. And so you see the arrow for the spring force is to the left. Okay? Okay, so that's a basic simulation right there. And I'm giving you the link to this little FET so that you can play with it yourself, okay, if you want to when you get a chance. Now, if we just look at this one-dimensional kind of problem right here, let's say that the elongation or the compression of the spring takes place along our x-axis here, and we put the origin of our x-axis at the unstretched location of the spring. So I'll call that the equilibrium position, and that equilibrium position is at x is equal to 0, okay? So if we do that, then we can write Hooke's law in this little 1D scenario right here as the force of the spring is equal to minus k times x, okay? So x is the position of the block in this case because I've placed my equilibrium position of my spring at the origin, right? So x is the position of the block at this case. K is called the spring constant of the spring. So if you've ever played with springs, then you know that some of them are stiffer than others, right? So the stiffness of the spring is the spring constant. It's how hard it is to pull or push on or compress that spring, to stretch it or elongate it. The units of that force constant, since you have newtons here on the left-hand side and x is of course measured in meters, then the SI units of the spring constant would be newtons per meter. So this F sub s is equal to minus kx is Hooke's law in one dimension. Okay, so that's a Hooke's law. Okay, so now let's look at a different FET. And in this FET, what I want to do is I want to show you a couple of different springs, okay? And yet again, I've given you the link to this FET. So here I have spring on the left here, and you can see it's a little skinny spring. So it's got a smaller spring constant. And then here the spring on the right, you can see, has, let's make it even bigger, a larger spring constant. So if I hang the mass, I'm going to hang a 100-gram mass from the left-hand spring, and I'm going to hang a 100-gram mass from the right-hand spring. And you can see that the one on the left, which is more loosey-goosey, it gets stretched and elongated more than the one on the right, which is stiffer, right? So it doesn't wiggle as far. That one on the right, it doesn't wiggle as far, okay? Now, another thing about it is that you can see from this little fet that I hung a mass on it, and then I kind of just allowed that mass to drop under the force of gravity. And then what happens is my springs are just sitting there and wiggling back and forth. So I told you that, if you give a spring a tug and let it go, then it would oscillate about the equilibrium position. And that's exactly what's happening here in this little fet. The little masses are bouncing up and down and wiggling, okay? Now, of course, a real spring would have some effects from friction here. And so, of course, eventually in a real spring, the amplitude of oscillation would gradually get smaller and smaller, and then it would eventually stop wiggling altogether, okay? But we've got this simulation, so we can turn all that off. I've got my damping set to 0, and so my little springs here are just going to wiggle forever, okay? So if you'd like to play with this fet, I highly encourage that, and we can talk more about those later. Now, if you were to plot what the force looks like, here you have F is equal to minus kx, right? That's our Hooke's law force. Then you can see that you have a linear relationship in between the force and the spring's displacement from equilibrium. It looks like a straight line here, all right? So this means that unlike the force of gravity or something like that, this is a non-constant force, okay? It's a non-constant force. It changes depending on the conditions, like where it is in its oscillation cycle, the force might be different. Because F is equal to minus kx, right, the force is 0 if the spring is at its equilibrium position. And then the force will be maximized when it's at the turning points, right? Like when it goes from going up to going down, that's its turning point. That's its maximum displacement, right? And at that point, the force is also at its maximum, okay? So the force is non-constant. All right, it's also important to realize here that because of the negative sign in F is equal to minus kx, the force is always going to be in the opposite direction from the displacement. So you can see here up in the top picture, x is positive. It's been stretched out to the right. And so the displacement is positive, but the force is negative because it's pushing back towards that equilibrium position. Vice versa, if the spring is compressed in this scenario, okay, then that means that your displacement x is to the left, right, which is negative, and your force is positive. It's to the right, okay? So always in opposite directions there. Okay, so let's figure out how we would write an equation for the motion of our little mass on a spring problem in one dimension, okay? So we can always apply Newton's second law. And Newton's second law says that F is equal to ma, right? So we're just looking at the x direction here. So here we have the force in the x direction is equal to the mass times the acceleration in the x direction. Now, by the definition of acceleration, that's equal to m dv dt, right? The acceleration is the time derivative of the velocity. But if we look at the velocity, the time derivative of the displacement, right, is your velocity, or the time derivative of your position is your velocity. So it would be ddt of dx dt, which gives me a second order derivative of my position. So I could write F is equal to ma, which is equal to m d squared x dt squared, right? The second derivative with respect to time of your position is your acceleration. Okay. So this is going to be equal to, for the spring force, minus kx. Now this is a little differential equation here. And I can rearrange my differential equation and say that the second order derivative with respect to time of my position here on my left-hand side, d squared x dt squared, right? That's equal to minus k over m times x. So this is the differential equation that we have to solve to find an equation that represents the position as a function of time for our mass on a spring system, okay? That's what we have to solve. Now, I'm going to give you a little tutorial here and now on how differential equations work. So if you end up taking the differential equations math class, I'm going to tell you right now in words what you're going to get out of an entire semester of differential equations, your first semester of differential equations. Here you go, okay? You look at the differential equation. You guess a solution. You plug it in and check it, and if it's right, yay, you solved it. Okay? I just saved you a lot of time. Now, I'm kind of kidding here, but I'm kind of not. That really is what they do in differential equations 1, over and over and over again for a bunch of differential equations. And yeah, that's it. So here we go. What we need is a function. X is a function of time, right? And if you look at this equation, what it's telling you is I have some function x of time, right, x of t, and I take two derivatives of it, and I get back some constants times -1 times my function again, right? So I need a function that if I take two derivatives of it, I basically get the function back with some constants multiplied out front and -1. Now, the truth is, there's a limited number of functions that that's true for, okay? If you think about it. And in the list that I can think of, the very first thing that pops into my head is actually the solution of this little differential equation. And that's sine and cosine functions, okay? So if you think about it, if you have a cosine function and you take the derivative of a cosine function, you get minus sine. And then if you take another derivative of that, then you get minus cosine, okay? So basically, you've got -1 times your function back again, right? Okay, great. So I'm going to guess a solution, right? I'm going to guess the solution to this little differential equation, and I'm going to guess a cosine. And I'm going to have my x as a function of time, my position as a function of time, be equal to, and here's my guess, a times cosine of omega t plus phi. Okay, so here omega, that's a Greek letter. I'm going with the Greek letter, conventional choice here. And phi right here is my phase constant. Now, remember that if you have a sine or a cosine function, then you have your argument plus some phase constant right here. What that does is it just basically shifts your function left right on your time axis, okay? So basically, when you started your clock at t is equal to 0, where was it in that sine or cosine function? And if you think about it, sines and cosines are really the same function, just shifted left and right. So guessing a cosine function with a phase constant in it could really be the same thing as guessing a sine function, all right? So I'm just going to go with the cosine solution here, all right? So here we go. This is my guess, okay? Now just go with me on this guess for a second. What I'm going to do is I'm going to plug it into my little differential equation and see if it works. Okay, so x of t is equal to a cosine omega t plus phi. If I take the derivative of that, dx dt, I get minus a omega sine of omega t plus phi, because the derivative of a cosine is a sine. So now if I take the derivative of that, I have the second order derivative of my position with respect to time. If I take the derivative of my sine function, I get a cosine, right? So now I have minus a omega squared cosine of omega t plus phi. Okay, but look, here I have a negative constant times my function again. So that would be equal to, this minus a omega squared cosine omega t plus phi is equal to minus omega squared times x, right? Okay, so there's x, a cosine omega t plus phi. Look, there's a cosine omega t plus phi times minus omega squared. That's it. So, great. Now all I have to do is figure out what the heck this omega is. So basically what I've got here, if I take the second order derivative of my position function with respect to time, that was my original differential equation, which is equal to minus k over m times x. So now I'm going to put in what I got when I actually took two derivatives of my guess, which was minus omega squared x, right? And then you can see that if that's true, what has to be the case is that omega squared is equal to k over m, or omega is equal to the square root of k over m. Okay? So basically, what this means is that we've just defined what's known as our angular frequency. Okay? That's our angular frequency. So the angular frequency is equal to 2 pi times the regular frequency. Remember, a frequency is the number of oscillations per second, right? So here you have your angular frequency is 2 pi times your regular frequency. And the number of oscillations per second, if you take the inverse of your frequency, you get a period, which is the amount of time, your period is the amount of time it takes to complete one oscillation. So here omega is equal to 2 pi f is equal to 2 pi over t. So I've defined now my angular frequency in terms of these things. And you can see that the frequency and the period are therefore dependent upon your spring constant and your mass. Okay? Okay, so just to show you that while it does kind of look like I just guessed at all of this, right? So what this would mean is that our motion is sinusoidal, okay? It oscillates back and forth. So I'm going to show you one more simulation, okay? Now here's a little simulation of the mass on a spring wiggling back and forth. And then on this page is a plot. Let me get rid of the velocity graph because that's just going to confuse everybody. Okay, so here's a plot of our position versus time. Okay, and you can see very clearly that that's a sinusoidal function, right? It's just oscillating back in time happily, right? And there it is. It's kind of hypnotic, actually. There you go. There's your cosine function. Okay, so the amplitude, look here, when it goes to red, it's compressed. When it's green, the spring is elongated, okay? So you can see that the equilibrium position is there or so, right? And so it spends just as much time compressed as stretched. Well, that's where the axis here bisects our little cosine curve. So our amplitude of oscillation is actually how far it's either pulled or pushed when it's at its maximum displacement from equilibrium. Okay, so that's our amplitude of oscillation. Okay, and it oscillates back and forth around that. Okay. Okay, so our amplitude of oscillation would be our max displacement in either direction, right? The phase constant is just where it is on this time curve, right? So where did I start my clock, for example? I mean, if my clock started right here, then it would be a straight up cosine function, right? And there would be no phase constant. But if it started at some other place, no harm, no foul, I can just slide my little curve left or right by changing my phase constant, right? When did I start my clock? Basically, that's the only question that answers. Okay? Okay, so we just introduced the idea of simple harmonic motion. So you have a mass on an ideal spring, and we're going to ignore friction, and that's called the simple harmonic oscillator. And sometimes people abbreviate it SHO, right? And this SHO is a good model system for a lot of things. We're going to revisit this in chapter 4 and in a lot of different chapters. That's why we're introducing these concepts early. So if you don't get everything right away, don't panic, right? We're going to keep coming back to this idea. And by the end of the semester, you'll do simple harmonic motion in your sleep, I promise. But the reason that we in physics emphasize the simple harmonic oscillator so much is because it is a good model system for a lot of things, like atomic bonds. And they're going to talk a lot about that in chapter 4 of Matter and Interactions. Okay? Okay, let's do an example problem because I really feel like it's worth a million words to do an example problem. So here we go. You've got an air track glider, and it's got a mass of 100 grams, and it's attached to a spring. The glider is pulled to the right by 20 centimeters and then released from rest at t is equal to 0 seconds. And then it oscillates with a period of 2 seconds. So, using this information, write the equation that describes the motion. And then, second, answer what's the spring constant of that spring. Okay, so just like any other physics problem, what you're going to do is you're going to first list out your knowns. So I wrote my knowns. The mass was 100 grams, which is 0.1 kilograms. So I put m is equal to 0.1 kilograms. My period is t is equal to 2 seconds. And my position at t is equal to 0 is going to be plus 2 meters. Okay? So here's what I need. I need to write my equation. Okay? Well, that also kind of solves what equation I'm going to use, doesn't it? Okay, that's nice. So x of t is equal to a cosine of omega t plus phi. All right, so this is a 1D problem. Let's define to the right as plus x. The t is equal to 0 position is going to be the maximum displacement from equilibrium. Well, if that's the case, then I don't need to shift my cosine function left or right, because by definition, a cosine function with no phase constant is at its max when t is equal to 0, because the cosine of 0 is plus 1, which is the maximum of a cosine function. So my phase constant phi is 0 here, okay? All right, now my amplitude would be 0.2 meters, right? So that's because I've given it its maximum displacement by pulling it to the right by 20 centimeters. So that means that it's going to oscillate back and forth between plus 0.2 and minus 0.2 meters. So that's my amplitude of oscillation, okay? So now I've plugged in for two of those numbers in that equation, right? A and phi. Finally, I've got to figure out what omega is. Well, I already showed you a relationship. Omega is equal to 2 pi f, which is equal to 2 pi over t. So my angular frequency is equal to 2 pi divided by my period, okay? So that means it's 2 pi over 2 seconds, which means it's pi inverse seconds. So my angular frequency is pi inverse seconds, all right? So now I can plug into my equation completely. I've subbed in all my numbers, in other words. I've got x of t is equal to 0.2 meters times the cosine of pi times t. All right, that's it. Now the next part of the question said, what is my spring constant? Okay, well, I have another equation for omega, which relates it to the spring constant and the mass. And that one is that omega is equal to the square root of k over m. So I know omega. Omega is pi inverse seconds, and then that's going to be equal to the square root of k divided by 0.1 kilograms. So solving, I would square both sides, and I would end up with omega squared is equal to k over m. And then I would multiply both sides by m. So that ends up being k is equal to pi squared times 0.1 kilograms, right? When I multiply all that out, I get a spring constant of almost 1. So it's 0.99 newtons per meter. So that's my spring constant, okay? So that's all there is to it. All right. Now you're probably thinking to yourself, or maybe not. Maybe you're just like, boy, I hope she hushes soon. But you might be thinking, what if it's 3D, okay? So if you had to write a spring force as a three-dimensional vector, which they do right away in matter and interactions in chapter 2, then to do that, we're going to define a vector and we'll call it L. And L points from where the spring is attached, which would be up here, down to where the mass is attached. Okay, so where the spring is attached to whatever holding it still, right here up on this board, down to where the little mass is. That's the vector L, okay? Now, the stretch of the spring would be the length of that vector L minus the unstretched length of the spring, which we'll call L naught. So here I've written the stretch of the spring S is equal to the magnitude of L minus L naught, okay? Now this is just generalizing so that you don't have to assume that S is in the X direction, the Y direction, or the Z direction. So I'm just making it general, right? It could be any combination thereof. So S for stretch, why not, right? Now Hooke's law can be written in 3D as a vector equation. So here we have F, right, the vector, is equal to minus the spring constant times the stretch of the spring times L hat, right? So L hat would be a unit vector that points along L. So basically, it's still minus k, the magnitude of the force is still minus k times the stretch of the spring, right? The negative spring constant times the spring stretched. It's just that now I have expressed this in a vector form so that I can do some simulations and good stuff with it, right? Okay? I hope that's clear. If it's not, let's apply it to the little problem that we just did, right? Remembering our last example, we defined our plus x-axis as to the right, right? And we said that the spring was pulled to the right, okay? Now, the magnitude of that stretch when we let her go was 0.2 meters. So since that's the stretch, then S is equal to 0.2 meters, right? Now, to the right was plus x. So if we pulled it to the right, then that's the direction that our vector L would point. And so that would mean that our unit vector L hat would be plus 1, 0, 0, right? Because it points in the positive x direction, okay? And the other components would be 0. Now the spring constant was 0.99 newtons per meter. So we could write our expression for 3D, F is equal to minus K S L hat this way, minus 0.99 times 0.2 meters times 1, 0, 0, okay? Using that unit vector notation that we've already learned. Okay, I hope that's clear. If it's not, let me know. And as always, I'll see you around in class.